Okay, we're at the bewitching hour, so we'll get going. I'm sure there's a few more people who will join us eventually, but this is, I think, the fifth in our series of webinars on ag energy topics. Today we're going to talk about energy conservation in greenhouses. In December we actually talked about heating with biomass. And we actually just, we're going to add a unit on in March. I think March 26th is when it's going to be held. We're going to add a unit on life cycle analysis. Dr. Reineman, who's at the University of Wisconsin, has been doing life cycle analysis on dairy and ethanol and stuff. And he's going to give us ABCs on life cycle analysis into March. So that's a webinar that will be added in the future. Today we're going to talk about energy conservation in greenhouses. My name is Scott Sanford. I'm a senior outreach specialist here at the University of Wisconsin in the Rural Energy Program, where I've been at for 10 years now. Let's see, I got to find my button disappeared. Hang on a minute. There we go. It's a thing you can put things behind things. So we'll get going here. So greenhouse energy use. I think this is a fun topic for me. One, because it's colorful. But greenhouse energy conservation or greenhouse energy use, it's usually about the third highest cost behind labor and materials. It's usually about 15%. It's been creeping up in the past year, although depending on what your energy source is at the moment, that may be reduced. If your natural gas has gone down in price, so you're at an advantage. Typically in the northern states, your energy costs, 70 to 80% is going to be space heating, about 10 to 15% electric, and then you're going to have some transportation fuels. One of the issues we've run into in greenhouse is balancing, with energy conservation, is balancing the agronomic requirements of the plants and the economics. So we can do things to reduce our energy use way down, but we would affect the agronomic or the growing of the plant. So we're always going to balance this, especially the light transmission for plant growth. And with different types of ways we can do it, there's structure and operating costs that kick in here too. So we're going to try to cover all those through this presentation. When we look at heat loss, it comes in 4 different forms. Conduction, which is a heat transfer through a material, and it's usually measured by U value, or you may have heard of R value. R value is the inverse of U value. And so building products are typically use an R value, which is going to be hours per degree Fahrenheit per square foot per BTU. So it's the inverse. The other thing we have is air exchange between a moving fluid and solid surface. That's convection, and that's going to happen in greenhouse no matter what we do. We can sometimes slow that down, but we basically don't want the greenhouse to be stratified because otherwise you get warm air on at the roof and cool at the floor. So we often mix them to avoid that. Then we have radiation. That's the heat transfer between two bodies without direct contact or medium transport. So that's typically sunlight. So sunlight will warm the objects, and then those objects, after they get warmed by the sun, if they're warmer than the surrounding air, they will re-radiate the heat that they've gained back into the greenhouse. So that's where we talk about radiation. And then there's infiltration, and that's the exchange of air between the inside and the outside through holes and leaks in the building, or sometimes it's planned ventilation. And because as new colder air comes in, we have to heat it up or cool it down, depending on what the requirement is. These heat loss phenomena are going all types of greenhouse, whether it's a hobby greenhouse or big commercial or just a single span. What's different is the economics. will vary depending on the size of the greenhouse. So the first thing I want to hit on is what I call structural efficiency. You know, if you're a new grower and you're thinking about building your first greenhouse, you can build two kinds. One's a gutter connected, and the other's a standalone. Gutter connected usually costs a little more, but it allows us to expand at a later date typically. So if we have a gutter connected greenhouse, and I've rated this on a half acre, about 25,000 square foot greenhouse, which is a medium-sized grower. I suppose that depends on where you are, but in Wisconsin that'd be a medium-sized grower. You'd have less heat loss per surface area because of the enclosed area. So it's about a 1.5 ratio of heat loss area to floor area. If I looked at covering the same amount of space with standalone greenhouses, my surface area would be higher, so I would have more heat loss. Now, on the flip side, the advantage is if I have a standalone greenhouse, I can have isolated growing conditions. I don't necessarily have to heat the whole greenhouse. I might have to heat the whole greenhouse and gutter connected if I didn't have it so I could partition it. So that can be a disadvantage. And I can better use natural ventilation sometimes with roll-up sidewalls. So the question I always ask people is, what shape has the lowest surface area to floor ratio? And it turns out to be a sphere. And if we look at the next smallest one, it's a square. So if we make a greenhouse in a square pattern, we will have the least amount of surface area per covered area. So here's my example. I got 24,000 square feet. I'm using a double polyethylene cover that's IR treated. So that's the best there is in the poly. I got some black cloth on the floor that helps absorb a little heat, and I got a power vent heater. So I'm looking at two different scenarios here. One is eight individual greenhouses versus one big gutter connected. And you can see from my example, there is let me get my pen here so I can do some colors here. Okay. So you can see there's an 18% difference in savings. Now, one of the things you'll see is I optimized this gutter connected so it was almost a square. So one of the take-home messages, if you're just starting out, you'd be better off with a gutter connected greenhouse if you're at all thinking of expanding, and most businesses, once they get going, end up expanding, is put a gutter connected up, even if it's one or two bays. They can be added on lengthwise, they can be added on sideways. So that gives you room to grow, as long as you don't put it up against the building where you're causing some trouble that way. The next thing is orientation of the greenhouse, so I can maximize sunlight. If I have a single span, the recommendation is the long ways, so east to west. So the long side would be facing the south and north. If I have a gutter connected greenhouse, then the recommendation is to run them north-south, and this is because I've got gutters in there that cause shadows. If I ran it the other direction, the shadow would basically never move all day long. So I have a spot in my greenhouse that never got full sun. So that could be an issue. When I'm looking at glazing materials, this has a direct effect on heat loss. I divided it up into two scenarios. One is a single glazing and the other is double glazing. And it actually doesn't matter what material we have. I'm picking glass here because it's the standby, and polyethylene film because it tends to have the lowest, it's kind of the shortest life. It's kind of the two extremes. A single pane glass is going to have a high heat loss. It also is affected by hail, but it has long life. So if the hail doesn't get it, it'll last a long time. It requires the highest cost structure because of the weight of the glass, but it has the highest transmission values. So if you're in a northern climate and you're really concerned about light transmission, glass is the way to go. On the flip side, polyethylene is lower cost, requires a lower cost structure because it's not heavy, but it has the lowest light transmission levels, and it has the shortest life. But it does have a very, especially if you use the IR rated, has a very, about half the heat loss. So that's an advantage. So we've got a chart here with the different glazing materials. First column is light transmission. And one thing you'll see is that it doesn't matter if it's a single layer, it's all about 90% or roughly. If I've got a single layer of glass. And if I'm doubling it up, I lose 5 to 10%. Actually, acrylic is one of the best, and that's one of the, it's not readily used, but that's one of the advantages it has. And my double poly is actually the lowest. The next is long wave radiation or thermal transmission through. So sunlight will come through, but will long wave radiation be reflected off the surface of it back into the greenhouse? And what I find is that double poly is pretty poor at that unless I have an additive. It's an additive they put in to do that. Here again, heat loss conduction. All the singles are a little over 1.1 to 1.2. So it really doesn't matter if I have a single or a double. Double is going to be half the heat loss of a single. Then the other issue over here is flammability. Some of these are higher than others. That's one of the things that acrylic has been poor at in the past, although there's new types out there that will meet the public's, there's a standard. If you're in a public building, it can't burn at a certain rate, and it does meet it now, the newer types. So that can be a concern. So we look at infrared radiation pathways. We've got the sun beating in the greenhouse. It goes through into the greenhouse. We do get some reflected off the surface. At the surface, it'll warm the objects in the greenhouse, and then they will radiate it out. Depending on the type of cover, so if I got glass or polyethylene, that long wave radiation will get reflected off the surface for the majority of it. If I have polyethylene films, about half of that will go through. It won't reflect off, with the exception if there's condensate. Condensate will help reflect or absorb re-radiated long-wave radiation. So when we do I'm going to skip this for now. We do polyethylene film. It's highly recommended we have the IR additive, and we only need one of these sheets. The outer layer can be a standard film. The inner layer will have an IR additive, and typically they double it up with an anti-condensate. So if you see AC in a name, that means it's an anti-condensate. IR or thermal is going to be have an IR additive. That will save you roughly 15 to 20%. Typically, it'll pay in one season, so it's well worth and it works out to about $10 a year or $20 a year on a typical 30 by 96 greenhouse. So it's well worth the cost. Now, one of the things is, we want to have that IR rated on the inside, and there is an up and down side to that material, so because of the anti-condensate, so you need to make sure that it's put on correctly. One of the reasons we're worried about what light is a percentage of light means a percentage of growth. So the transmission level through that glazing material is important. So there's a wide range. Anti-condensate or condensate can reduce the light, so that's one reason we want to keep the condensate off the films. Now, we can, if we didn't get an anti-condensate, or if we have say a glass or polycarbonate, there is a spray-on anti-condensate material we can use. In some parts of the country, dust is an issue, so they do have dust additives. I apologize. It seems like there's a lot of people that are having problems staying on the call. I'm not sure what the problem is, but hopefully people are being able to stay on the call. And if you're having problems with the VoIP, you can go up and there's an 800 number I put on there. You can call in. So glazing materials versus infiltration. Basically, they're related, because the more joints you have, the better the chance that you're going to have leaks. So, we have already a lot of leaks in these. We have louvers, we have doors, we've got intermittent holes, we've got lapsing glazing. All those are places where we can get infiltration losses. Glass is usually about 2 times what a polycarbonate will, just because of the number of leaks in the system. Anywhere time we have one film or one cover, such as a poly film, that's going to be the lowest. And these are the generally accepted numbers. They can range way outside of this depending on the condition of the cover and how well it's maintained. One of the things we can do to reduce infiltration losses is to try to reduce the wind speed. As the wind speed goes up, the infiltration loss will go up. So one of those things we can do is windbreaks. So we can use trees is one possibility, or we can build some kind of a structure. Windbreaks have a couple advantages. One is reducing the wind, reduce our losses by 5 to 10%. Also, if they're placed properly, they can reduce snow accumulation on the greenhouse and reduce wind. We do want to get those far enough away from the greenhouse that the snow does not end up on the greenhouse. So that is an important factor. Infiltration leaks, we can save 3 to 10% in heating costs by fixing these, and more than that on a glass pour glass greenhouse. But we're looking at roof and wall vents to make sure they're tight, make sure cover's tight, lap seals on glass, fix holes on cover, weather stripping around doors. And one of the reasons I have this picture, this top picture here, is this is a corrugated roll-up door. These are terrible because they're almost impossible to seal along the edges and across the top because of the corrugation. So my recommendation on some of these is to go on the outside, put a wiggle wire strip around the outside, and seal it off during the winter, especially if you're not going to use it, because they're terrible at leaking. Door sills. The other is the sill plate on the greenhouse. That's the other picture here. You can get leaks under the sill plate if the dirt isn't up against it to seal that in. So all these things add. Louvers, if you're not going to use them during the winter, close them tight, put a piece of plastic or foam over them. If we have a leaky glass greenhouse, one of the emergency things we can do is just put a piece of polyethylene over it, and we can reduce our infiltration losses by 40%. Conduction heat loss. Typically, we've already talked about the glazing part of the materials, but very often we have opaque walls on some areas. So we could insulate the side walls up to plant height. We don't care if there's light underneath the bench typically, so we can insulate the wall. If you're going to put foam board against the wall, say you got a poly or a polycarbonate greenhouse, you got to make sure that insulation is sealed to the wall. If it's just sitting there, it's not going to do anything. It has to seal it so there's no air movement. North walls. If we have insulation, opaque walls, we can insulate them with 1 inch or 2 of foam. If you're building a new greenhouse, putting in 2 foot or more of 1 to 2 foot of foam insulation around the perimeter would reduce heat loss. It's really hard to make it cost effective to put it into an existing greenhouse because of labor cost unless you're trying to grow on the floor. Then it may be worthwhile because you're losing growth next to the floor, next to perimeters because of the cold floors. So in that case it might be worthwhile. One of the things, the technologies we can use to reduce heat loss in a greenhouse, even if you have a double poly cover, is to use energy curtains. And in its simplest form, this is looking at a heat cover, it's just some kind of a blanket that covers the growing area. It has to be sealed on the edges. It's got to be supported someplace above so it doesn't crush the plants, and otherwise it's just a cover that goes from end to end. So one of the reasons these are effective is because 80% of our heating is at night in a typical greenhouse. And these can reduce heat loss on a greenhouse by up to 50%. Basically, they add another thermal boundary layer. So if we look at a double poly with a curtain and without, so without a curtain we're about 0.7, with a curtain we're about 0.4. So that's not quite 50%, but it's close to it. And then again, they can double as a sunshade during the summer. So if we're growing year-round, they can help do that. And for a sunshade, they can lower temperatures underneath the curtain by 10% or 10 degrees Fahrenheit or so. And if you have an internal shade cloth, they're basically can be used as a thermal. Anything we pull over there, even if it's porous, will help reduce our heat loss to some extent. The cost of these between $2 and $5 a square foot. So depending on your fuel cost, sometimes it's tough if you're just growing spring bedding plants. Sometimes it's tough to rationalize them, but they do save energy. Automated systems can be used for large greenhouses, or you can make a manual one. You can have some rollers or some wires and basically just hand pull the cover over the plants at night. So I'm going to give you some examples here. We've got a 30 by 120 foot gutter connected greenhouse with 6 bays, so about 2,100 square feet. We've got double polycarbonate. We got $1.50 for propane, and that's how much it cost me. About $20,000, $21,000 to heat it on a typical February to June growing season. The thermal curtain we've got covers 100% of the roof with a 52% energy saving. So basically that will save me 35% in energy costs by putting that curtain in, about $7,100. So I look at a freestanding greenhouse. Here I'm looking at 90% of the roof covered, 50% of the gable ends with the same cover. I'm at 32% savings. So they are going to be in that 30 to 40% in a seasonal savings typically. Types of systems we have, you can do gutter to gutter. So if you've got a curtain, you can go from gutter to gutter across, and you can go down the linear side of the greenhouse, which is more common these days. So they go across the bottom truss, and one of the things, they reduce the volume. So all this air above the curtain we don't have to heat at night. So that's an advantage. And these type of curtains tend to be the lowest cost to install. However, growers like to hang things from the purlins of a greenhouse, so the industry has come up with 2 different designs. One's a slope flat slope, so it slopes up, it goes across the flat, it slopes down again, and the advantage is you can hang all your stuff you want basically over the growing area, and this will reduce heat loss, reduce volume somewhat. You've got a little less volume, but allows you not to have to move the expense of moving the equipment. Then there's a slope, and the advantage of that is when I go to open these in the morning, all this cold air above, I've got to warm up before, otherwise it's going to affect my plants. So this slope has the least amount of cold air above it. So here's an example of what a flat slope looks like. So a slope up here, it goes across the flat and then down the other side. So you can see this air duct I could put above there, or the poly tube we could put above there, and we've got some plants hanging from there. We didn't have to move any of that to put this unit in. So that's when it looks with it partially open. This is what it looks like when it's closed. It folds up in this little spot. So it does add a little bit of shading, but not a whole lot. But the big gain is in the fact you're covering the greenhouse. There are 3 different types of materials that can be used. There is a non-porous material, so you could use a sheet of plastic for this. It'll have the highest heat retention value because it doesn't allow any air to go through. But the one problem is it's impervious to water. And that's a problem because we do often get condensation off the roof when it's closed. As it cools down, we'll get condensation. And if that collects on top of the curtain, it can cause the curtain to fail. So the industry has gone to what they call semi-porous material. It's basically, if you think of a blue tarp that you can go and buy at the hardware store, it's a woven material. But those tarps that you buy at the hardware store have a coating sprayed on them to seal them, to make them waterproof. These aren't waterproof, but they're tight. So they don't allow much air to go through it, very little, but they will allow water to migrate through it. So that's an advantage because they won't fail, but they still have the same high heat retention value. The other is a porous curtain that allow air to go through readily and allow water to go through. It has the least amount of heat retention. So this is like a luminette would be an example of a porous curtain. These can be used as sunshades in the summer, and basically the higher the shading factor, the higher the heat retention value for these materials. So here's some examples of materials. We're going here from the least amount of reflectance value or shading value to 100% over on the left. So we've got 85. Anytime you have a piece of material, you're going to have some shading. So even a sheet of clear plastic is going to be about 10%. So here we go. 45, 35, 25% light transmission through them, and to 0. And you can see that these have aluminum strips in it, and basically that helps reflect the heat, especially long-wave radiation heat, back into the greenhouse when it's closed. As I said, the light transmission is related to energy savings. If we go all the way up to a blackout curtain, basically they're about 70% energy savings. Luminette, which is a type of sunshade, it's basically made out of aluminum. Those are 50%. Those are only going to have about 20% energy savings versus the semi-porous, which will be about 50%. If I take that same curtain material that I had back here, they also make them where these open strips, they don't put any material in there. There's no luminize. It's open to let air migration through that. That would be what this column here is, and you can see as soon as you open that up, this one's about the same as that. My energy savings drops drastically because I allow the air to migrate through that curtain material. Now, so the question is, what material is best? Well, some of it depends on the amount of energy saving I desire, and if I'm doing an amount of shading I need. If I'm doing something like poinsettias, I may have a full blackout curtain because they're very sensitive to light. Or maybe mums, I might need a full blackout curtain. But if we look in the maximum sunlight during the summer is about 10,000 foot candles. It can be higher on a very clear day. Most flowering and bedding plants can only tolerate about 4,000 to 5,000. If I take off my light transmission, I get reduction going through the greenhouse, and that's just the materials. I also have all the structure in there that blocks light as well. So if I take that 10,000 foot candles, I multiply it by my double poly, and I take my light transmission for my curtain material, I'm going to end up with about 4,400, which is right in this 4,000 to 5,000 foot range. So something with about 45% shading or 55% light transmission is going to be about 50% energy saving. That's about optimal for most people for a good all-around curtain that can be used both in summer and winter. Here's an example of a grower-installed curtain. This is in a Gothic-style greenhouse. This doesn't cover the whole roof section, but it covers basically from the purlin over here to the purlin on the other side. It's got a hand crank. This is a rod that goes across the top. The cables, here's a cable going right here, that wrap around that rod, and basically with a hand crank we can open and close this curtain from side to side. So it's just an example of what might be done. This is a suspended type curtain. I probably should have mentioned that you can have suspended or you can have one that lays on top. But I left that for now. That's a detail on how the curtain's put together. But the main thing I'm trying to get across today is they do have a pretty good energy savings to them. The next thing is I look at is greenhouse unit heaters. There's two types of heating. Basically, you can have a centrally located heater or some kind of a unit heater. So I just want to go through the unit heater briefly. They're very popular, especially in standalone greenhouses. So one advantage is they're low cost, they're easy to install, low cost of installation, they're easily staged, and very reliable for the most part. There are several types. There's on the top right here, we have one that's a gravity vented, and they can be told there's basically a pipe that comes straight out of the back of the heater to the outside. The next step up from that is what we call a power vent, which is on the bottom right. It's got a little fan unit here that when the heater comes on, the fan starts up, and it actually forces the draft or meters the air for combustion through the heater. In having that fan in place, it reduces the losses that would normally go up the pipe on a gravity vent. Now, in both these cases, we're pulling air from inside the greenhouse for combustion air. The next step up from that is what we call separated combustion, where it's a power vent. Here's my little fan on top, but it also pulls air from the outside for combustion air. So the advantage of those is whatever the rating is on them is what you get in the greenhouse, because all the air from there's no air from the greenhouse that's used for combustion air. The newer thing on the market, which is, they've been around for maybe 10 years or so, is a high efficiency or condensing type heater. These are over 90% efficient. Basically, this is the vent and the intake pipe here. They can be plastic, and they do have condensate. The way they get higher efficiency is they condense some of that moisture that happens when we combust a material. We get moisture, and it condenses some of that out in an additional heat exchanger to get more heat out of the exhaust air. So we're going to do a little comparison here. So if I look at their labels, basically, the first three, the thermal efficiency or the instantaneous efficiency, they're all 80%. And this last one, the high efficiency, that's 93%. Gravity vent heaters are no longer available. I think it was the 2007 Energy Act basically made them discontinued. And we'll talk a little more about that in a minute, because you can upgrade them if you have one. But But traditionally, they were about $100 difference in price from a power vent. Then we have separated combustion, which is quite a bit more, and we have the condensing unit. These may have been quite a bit more because of material. Some of the higher end heaters will have these stainless steel heat exchangers, which are highly recommended for a greenhouse versus just an aluminized heat exchanger. When I look at these different heaters, the other thing we want to consider is the seasonal efficiency. And that includes heat loss out the exhaust vents or out the flue pipe, and when it's idle, and also pilot light use and air use for combustion. Well, if I look at that in a gravity vent, all of a sudden this drops to about 65%, whereas my power vent is 13% higher at 78%, just by getting rid of that air that leaks up the exhaust pipe. I've increased my efficiency by 13%. Then I can gain another 2% if I pull in outside air versus using combustion air inside the greenhouse. So my gravity vent and separated combustion, basically the seasonal efficiency and the thermal efficiency are identical. So if you go to buy a heater nowadays, the only thing you're going to find on the market is a power vent, which is 78% efficiency. And we're going to look here in a second. I think. Well, I'm going to do an example here. So let's look at these two different types of heaters. We'll look at all of them. So I got a 30 by 96 greenhouse standalone. I'm going to use 2 LP heaters. One can supply heat 90% of the time, and I need that second one for 10% of the time. So that's how I'm going to size them. Daytime of 68, nighttime of 60, $1.15 for LP gas, February through June. So if we look at that example, and we use the gravity vent as my baseline, that's what there's still a lot of them installed. I need 2 heaters, so the incremental cost of that is $180. The next step up is a separated combustion, so the incremental cost on that for 2 heaters is $3,200. And then if I go to and then I got the high efficiency condensing heater. So that's if I use 2 high efficiency heaters, the condensing type. That's going to be almost $4,000 more. But then I said, well, since one runs 90% of the time, if I stage them and have my high efficiency condensing unit and a power vent together and make the power vent so it's the second stage, that will reduce my capital cost, but I get most of the benefit. So that's only $2,000 difference. So here's this is my fuel I'm going to be using, and this is based on a model. So I'm going to 16% less for power vent, 19% for separate combustion, and 30% for a high efficiency unit condensing, two heaters, and 27% if I replace one of those high efficiencies with a power unit that runs 10% of the time. So here's my fuel savings in dollars, and if I take my fuel savings and divide it into my incremental cost, that gives me my simple payback. So the power vent is going to pay off in 2 months. My separated combustion is going to be 4.6 years. My 2 high efficiency units are going to be 3.5 years. My 1 high efficiency unit and 1 power vent is going to be 2 years. So the moral of the story here, and I'm going to look at it compared to power vent next, but get a high efficiency condensing unit at least for your initial stage, and use your power vent for your second stage. It's going to be the best bang for your buck for heating a greenhouse. Now, if I use my power vent heater as my baseline, then all of a sudden it really changes the economics. My separate combustion is outlandish because of the high incremental cost compared to my energy savings. I only get 3% energy savings. But when I have 1 high efficiency condensing and 1 power vent is still very good investment. That's basically a 20% return on investment. Okay, if you happen to own a power vent heater on a greenhouse, the good thing is that some companies have conversion kits. So I think this one was from a Modine unit. So you can convert them for about $483. So you're going to pay that back in a season or two with that 13%. So it was about $600 savings per year. So it's going to take you, you're going to pay that in a season, depending on where you are and how much it runs. So that's a good thing. They just bolt right on. Now the other type of heater out there is called a non-vented heater. LB White's one. There's a couple of other different models where all the products are combustion. It's very very clean burning heater. All those products of combustion go into the greenhouse. So from a thermal efficiency standpoint, they're 99% efficient. When we look at a seasonal efficiency, they're less than that. And the reason is, if I look at the last bullet point, you must have fresh air intakes. I have to bring fresh air to replace the oxygen that I'm using in that greenhouse. Otherwise, I'm going to affect plant growth and I'm going to affect human health in that greenhouse. And if it goes far enough, I'm going to get incomplete combustion. The other thing is these are often sold is that they increase CO2 levels. Well, it's great during the day, but plants don't use CO2 at night. So one of the recommendations, if you want to use one of these, use this instead of your power vent heater. Use a high-efficiency condensing unit at night. Use the power vent or one of these non-vented heaters during the day for heating. So you flip which is the primary stage day to night, and then it acts as a CO2 generator to provide heat during the day. Because one of the issues is that all the products of combustion go into the greenhouse, including the water. So it can create, depending on your air exchange rate, it can create a high moisture conditions, higher moisture than you'd like, than you would have if you had a unit that is a vented unit. One recommendation is that we don't use portable kerosene or oil type heaters. These salamanders and stuff, it's even for emergency uses. If you're going to use them, get one that burns natural gas or LP because they're a bit cleaner. But these are meant for places where, to provide a little bit of heat to take the discomfort, because one of the big problems, besides the products of combustion, they don't necessarily burn the cleanest. But the other is, if they're oil or kerosene, they give off ethylene, and ethylene will affect plants. Depending on the type of plant, they can be very sensitive to it, especially tomatoes, but there's other flower plants, and you won't notice the effect until 2 to 3 weeks later after you've burned that, used that heater. So they're not recommended. Now, the next thing we want to look at is heating distribution locations. Anytime I can make a microclimate and get the heat down underneath the plant instead of heating this whole greenhouse, I can save energy. So we can do that with in-floor heating, where we grow things on the floor. So we can have a concrete or dirt floor with heat pipes in it or on it. Typically that's a hydronic or hot water heating system is used there. We can use an underbench or bench type, and that's what's pictured here. This has got little capillary tubes on the bench for heating. And this can be hydronic, similar to this system, or it can be forced air, where you just have you could use a poly tube underneath the benches to provide that air underneath the bench. Studies have shown a 7% increase for yield in tomatoes on this. Basically, you'll get better plant growth and stuff for this. And it's essentially equivalent to turning down the thermostat in the greenhouse by 5 to 10 degrees. Because we only need this little microclimate to be 70 degrees. We don't care about up here. and that can be 50 degrees. We really don't care. We just care about where the plant's is grown. And here's an example of the heat distribution. We have the bottom picture is without, well, it's just perimeter heating, so all of our heating is over on the outside. We don't have benchtop heating. And you can see the warmest temperature, the coolest temperatures on the floor, the warmest temperatures up here on the ceiling, whereas if we have benchtop heating, we have this nice microclimate in here, and it's cold on the ceiling. Because we don't care if that gets cold. We want this zone here where all the plants are warm. So the potential is we could essentially save about 50% of our heating costs. Now, one of the issues with benchtop or in-floor heating is we often need additional heating units because in very cold weather we often can't get the heat transfer we need for that. So you still will need unit heaters probably. And here's an example of a grower who took a heater. This is actually not a propeller. This is a blower-driven unit heater. Many of them are propeller-driven. This is blower unit. And he's basically ducked this down under the bench and has a poly tube on it. I couldn't really get a good picture of the poly tube, but ducked it down underneath the bench to provide under-bench heating. Here's an example of a under-bench heating. So here's a fin tube design. This is a purchased product. It's got a couple fins that gives off low amounts of heat to distribute the heat under a bench. And these actually are moving benches, so they're rolling benches. And then here's a homemade system where they took some black pipe to run some heat underneath. And here's another homemade one where they got radiator type. This one's going to give off more heat, but where they just had radiator type pipes running through underneath the bench. So all those are options to use. One of the issues is getting the right amount of heat. Heating maintenance is important. One, if we've got a head house, insulate the pipes and ducts in the head house because we don't really, usually we're not growing in those areas, so we don't really want the heat there. We need to clean heat exchangers on a yearly basis. Make sure the motors and fans are lubricated and clean. Remove soot. So if we've got a boiler, we need to clean out those heat exchangers annually. If I got steam system, which I don't think there's too many, but steam trap maintenance is very important. Burner tune-up. If I've got oil, especially, but even if I have LP or natural gas, we want to check those boiler or those nozzles and the fuel filter to make sure that they're clean. So on an oil boiler, we're going to change the fuel filter yearly and make sure the nozzles are clean. If we've got a thermostat, we want to make sure that's accurate because there's nothing worse than having a thermostat that's not accurate. Then you're not going to get accurate heat. But if we do all this, the potential is in some very bad cases is 20% energy savings. It's usually always worth the cost of having a professional come in and tune up your boiler. One thing I will point out is if we have a boiler in the greenhouse that doesn't have outside air intakes, if I'm in there on a cold night and I smell the products of combustion, I don't have enough air intakes. That means I need to do something for air intakes for those boilers because I'm starving the boilers for fresh air. And essentially I'm pulling flue gas back into the greenhouse. There are high efficiency boiler systems out there. These are called modulating boilers for the most part. Here's two examples of some. So this one they retrofitted into a greenhouse and they didn't have any place to put it, so they put it right in where the plants were. It's very small. So these are hot air system or hot water systems, 90% plus. In fact, actually, I think this one here was 98%. So very high efficiency. And there's lots of manufacturers out there. There's not just a couple for this type of boiler, because these types of boilers are used in many types of buildings heating as well. If I have a hydronic system, I want to say I want to get one of those high efficiency boilers. The way I can get my heat into the greenhouse, I can use a water to air exchanger. especially if I'm using underbench heating and I need that extra way to get heat into the greenhouse on a very cold night. I could use one of these air-to-water exchangers. Infrared and radiant type heating systems have been used in the past for heating. They basically heat the objects in the greenhouse, not the air, so they're very efficient in that regard. You need to be careful with these. There's a couple companies that have tried to push them, and here's one of the companies. I gave you their link to a publication they have. But the concern here is burning the leaves, the plant leaves. I can get these too hot and basically burn the leaves. And there is issues with heat distribution that varies along the pipes, so I don't always get even heat distribution of them. Where they are really great is in the warehouse, loading areas, work areas, where I'm not growing plants. But that's just, I've been in greenhouses that have them, but that's just a word of caution. They have to be managed properly. Environmental controls. One of the concerns here is, one, especially heaters and fans fighting themselves, so we don't want the heater come on, it overshooting, and then or going above the thermostat for the fan, and the fan turns on, because then we get cycling and we increase our energy use. So that is a concern. So one of the ways to do that is a central controller, and they can do more than that. They can control louvers, they can do irrigation, lighting, CO2 generation. Basically, you want to ensure that no systems are competing with each other. And these can be tied to some of the more advanced systems, can be tied to weather data. So it can be tied to wind speed. So if the wind comes up and your vents are open, it may close down the vents and turn on the fans if you're trying to do naturally ventilated. The other thing we can do is what we call diff, where we have a difference between day and night, and then there's reverse diff where I can make it warmer for a few hours at night and cooler during the day, and that can affect how much the plants elongate. So I can do things like that. So one of the things with plants is they actually just look at the average temperature as long as we're above or below the maximum or minimum temperature the plant can withstand. So if I have 75 during the day and 65 at night, it's the same as being 70 all the time. Well, that's equivalent to, at 10-degree diff is equivalent to a 5% energy savings. So just by changing my thermostats, I can save energy but still not affect plant growth. So that can be an advantage. Whoops, not too many here. The other thing we want to look at is space utilization. The more plants I can stuff into this heated space, the more revenue I'm going to get out of that heat, or the more I'm going to utilize that heat. So when we look at a longitudinal or traditional type bench design, I get about 59% space utilization. If I use a peninsula type, I get about 69%, but if I use a removable, or I just have enough, I have a little alley here for working on the two benches that I'm going to work at, I can boost that up to about 81%. This movable isn't very good for retail space. The longitudinal peninsula I could use for retail space. So there's now one of the things I could do is a movable bench. If I had them on rollers instead of a rolling bench, if I had them on wheels, I could actually, got down around retail space, take a few of these benches and stick them outside, and turn it into a peninsula type design for retail sales. So there's some things we can do there to maximize our growing space during the system. So here's an example of a movable type bench. These are a roller. They actually roll on a pipe. Here's the pipe right here that it's rolling on. It runs the length, and basically this will roll back and forth. I think it's about 18 inches. So it's enough for somebody to get in this work alley and work on both sides. You can work on half a bench. And this one actually has irrigation pipe on it, and here we have the underbench heating with these. So just to show you an example of what can be done. The other space utilization is racking systems. This can be on the floor or overhead. We could have the plants that require lots of light hang from the ceiling, and ones that are shade-loving underneath them. Those are just some ways that we can take advantage of different light and temperature requirements for different plants. So in recent years, these hanging basket systems have become popular. There's two types. There's a cable type and a pipe type. So you can get lots of plants overhead while still allowing enough light to come down. This one actually you can have different levels. So and this one's showing you've got a water system right here in the middle. It's hard to see, but there's a water spray head right there that's watering this plant. So they can be automated once they get set up to move the plants around. With these pipe systems, they cover half the greenhouse, so you can move them from end to end, so you don't shade the plants underneath it all day long. Circulating fans, they are good for mixing air because we want to prevent stratification. So that can reduce heating because now we get we don't get stratification of the heat on the ceiling. We can get that all the same temperature. So we're usually going to use some kind of fans along the wall or someplace. And we usually like to get a circular pattern. So if I've got the greenhouse here, I want to push the fans along this wall that way and this wall that way so that I get the air moving in a circular pattern. There's some companies that have come out with these jets that push the air down. They're useful too for destratifying air. One of the big advantages of doing this also is I get increased drying of leaves. So if leaves get wet, they get dried faster and reduce disease potential. Let me hit on energy efficiency just quickly of fans. We have exhaust fans typically in greenhouses. And the efficiency can range widely. There can be a twofold difference in the efficiency of fans. The good thing is we have an independent testing lab at the University of Illinois that tests these things and publishes the data. So if you go to this website, you can get the data for whatever fan you want to look at. What I recommend is you look for fans, for exhaust fans, not circulating fans, exhaust fans of 20 CFM per watt or higher. And typically larger fans are going to be more efficient. So, I might have a large fan diameter and then put a variable speed control on it so I can handle that with different air flows. So that's one possibility. A little maintenance thing on fans. One is shutters. If they don't open and close properly, they can reduce airflow. Want to clean them and use a dry lubricant like a graphite. Belt tension on them is important. If we have a slipping belt, that can reduce airflow by 30%. So you're spending the money for the electricity, but you're not getting the airflow. And I recommend if you're going to buy new fans or retrofit a fan with automatic tensioners so you don't have to worry about them. The other is getting the weeds and brush or anything that would occlude the air from leaving the fan. Get those out. And most fans don't require lubrication of bearings, but they used to. But one thing we do want to do is have totally enclosed motors because it is a wet environment in a greenhouse. We look at ventilation. I'm not going to get into it too much because concentration here is on heating, but we can use shade curtains for cooling, get 10% reduction in temperatures underneath. We can use evaporative cooling pads. We can use misting. We can use roll-up sidewalls. We can use open roof designs, which is what this picture was trying to show. Here's an open roof design on a greenhouse. And we can use variable speed thing. And then here's another one. This is a greenhouse. You've got an open top, and these are blow-up sidewalls that will open so you get natural ventilation up to the greenhouse. Here's another picture of the open roof design. Great. You can ventilate a very large area. This particular greenhouse I was in, half acre, no fans. The air was moving through like you had circulating fans. So one of the disadvantages I see with these is you've got lots of area for leaks here because of the openings, and depending on the model of the greenhouse and the age, they may or may not have any seals on those. Here's one with inflated walls that I mentioned. These walls inflate or deflate to open and close, along with a roof vent that opens to get natural convection up through these. Roll-up sidewalls can be great for, especially for single standalone greenhouses, because I can roll up the sidewalls and I can get lots of air movement through this greenhouse. The disadvantages of roll-up sidewalls are they're typically single glazed material and they have high infiltration rates. So what I recommend is you get some wiggle wire and put that around the outside. So when, in the wintertime you seal those down because you're not going to roll them up the winter. You seal them down, and actually you might even take two wiggle wires, put one on the inside, one on the outside, and add a second sheet of film so that you reduce the infiltration and possibly can blow up that, put a little air into that to get your reduced conduction or conduction heat loss as well. Supplemental lighting can actually help us, and basically it shortens the time to market. Yes, we do have an expense to run the light, but if it's the right type of plant, we can actually reduce our production time. So maybe instead of starting the 1st of February, I might be able to start the 15th. Basically eliminating 2 weeks of heating. That can be a huge advantage. So I can plant later, have less heating, and sometimes earlier flowering. So it depends on what you're trying to do. Lighting has been shown to provide more root development if I'm looking at plugs. And we can do controllers, and I talked about the controller earlier. We can have controllers so they effectively measure the light level, and if it didn't get enough light level in the greenhouse during the day from natural sunlight, it turns on the light to get a certain amount of light interval or moles of light. This is, if I'm doing leafy lettuce, like leafy lettuce products, they have a high light potential, and it's one of the ways I get my product turned every 35 days to market is by using supplemental lighting. With growing chambers, I can use T8 fluorescent lights. They're going to be the most efficient type of light. If I'm in a greenhouse, I can use HID type lights, typically high pressure sodium or metal haloid. I might use them on a 50-50 mix. There's potential you could get off-peak electric from your electric provider to power these if you're lighting them at night. And I don't have it on this, but LED lighting for greenhouses is also coming. It's still kind of in its new infancy, but that has a potential to reduce your cost of lighting by 50% potentially. Just a few slides on solar greenhouses. I often get calls for solar greenhouses. I want to build a solar greenhouse. My response is greenhouses are solar because you've got light coming in them. That's one of the things that heats them up. Well, essentially what they want to do is avoid heating them if they can. So in that case, you need thermal mass. You need water, rock, stone, brick, something to absorb the excess solar radiation during the day and release that at night. Cornell University did a study some years ago and looked at a rock bed underneath the greenhouse tables and found that they could replace about 25% of the nighttime heating with a traditional kind of passive. They had a fan on it to blow the air through the rock, but passive heating. One of the issues that people often don't understand is that the temperature is going to have to vary more than it would be in a typical heated greenhouse to use this. So during the day, you have to get the heat above what the thermal storage temperature is to drive heat into the thermal storage, and at night, you have to let it drop below the thermal storage temperature to get the heat out of the thermal storage. So you're going to have a lot wider temperature swing within that greenhouse to do that. And the other thing is that if I do use supplemental heating, it's going to take longer to increase the temperature in the greenhouse because I have to heat the thermal mass to get the temperature in the greenhouse up and stable. So that is a disadvantage. So if you're interested, Solvia is one of several books that's out there on passive solar. There's also a passive solar energy handbook, a couple books that you might look for to if you want to read up on more. Some of the features of these greenhouses are a south-facing glazing. So this side of the greenhouse will be facing south. Typically, you've got insulated west, north, and walls and roof. So the sun in the wintertime is at the low level, and will come through the greenhouse and hit the back wall. So that's where I typically would put my thermal mass, and I might have some in the front here, and then I've got my growing space in between that. In the summer, if I do them right, so in the wintertime I can reach the back. In the summertime, depending on what latitude I am, the sun won't hit the back, the thermal mass, and I can use shading on here too to use it during the summer as well for growing. So here's some examples. This one's in western Pennsylvania. It's heated by the sun and some firewood, so you have some supplemental heating for this one. This other one, that one's in Nantucket. This one's in Nantucket, so that's a little warmer climate. Being it's surrounded by ocean. Here's one in the Rocky Mountains where they have, this one actually has 2 stories. It's hard to see, but there's actually you've got a growing area down here, and then another growing area up here, and then this is their kind of their work area in the back here. So here's some examples of what that kind of looks like in the inside. Not very well organized, I would say, but so here they're putting some of their heat-loving plants next to the thermal mass. If you have a greenhouse and you want to look at the energy-efficient options, you can go to this. This is a tool that we put together here at the University of Wisconsin. If you go to this website, actually you don't need the last 3 letters, but if you go to that website, there's a greenhouse tool here. And if you can enter the information off your greenhouse, it will pull in some weather data based on your zip code and spit out estimated energy usage, and it will give you some estimated savings for different energy-saving technologies, such as high-efficiency heaters and thermal curtains and double glazing and things like that. Here's some other resources that you might find handy. This energy conservation for commercial greenhouses is a very good one. Quite a bit of today's presentation was out of there. And if you're interested in lighting, this is an excellent publication. It's Lighting Up for Profits, because it talks about different types of lights. So Eric Runkle, he's still doing lighting. He's at the Michigan State University. I think Paul Fisher's down in I think he's at Florida State. But they put together this publication, edited it. Lots of people have contributed to it. But it looks at what plants can be affected by light, what light levels are needed to increase or decrease production time. So that ends what I had to say today. If anybody has any questions, I can entertain them now. I will be sending out an evaluation here in a little bit to basically a post-evaluation. I appreciate all those that did the pre-evaluation. This presentation was sponsored by SARE, which is a USDA program, Sustainable Ag and Research and Education, by Department of Energy through the Wisconsin State Energy Office. There's a grant called the State Energy and Extension Program Initiative, and the University of Wisconsin Extension and the University of Wisconsin-Madison. So do anybody have any questions? I think I see one. Let me see if I can get to it. Well, I thought I saw a comment, but I don't see anything coming through here. Well, if you have a question that you think of afterwards, Willis, future viewing, yes, this has been recorded. We'll eventually get it posted. It will, I believe a link will be sent to you at the conclusion. It takes about a half hour or an hour, and there'll be a link to the presentation sent to you today. And eventually it will end up on the e-extension website, extension.org. Are there any other questions?